Hi friends, so welcome to a new segment. We will talk about complex numbers and its uses in vibration analysis. So in the first optional video, we saw the few concepts regarding to complex numbers, and we talked about what physically happens to a complex number or geometrically happens to a complex number when we multiply it with other number. Then we talked about two ways of representing a complex number. One was the r theta form and the other was a plus ib form. And see, if you are quite confident with the theory of complex numbers and their interpretations, then you can skip this video and you can move on to the next video. This is intended at those people who may have forgot what they were learned and who may have missed a bit of physical intuition into the dealing of complex numbers. So let's get started. So here again I have a real imaginary plane. So let's say I will start with a arbitrary number. This is a purely real number, but let's call this is a complex number. This is 3, so I can represent it like this. So the magnitude is 3 and my phase angle is 0, so it is shown here like this. Make sense? Now what I'm trying to do over here is that I keep my magnitude constant and I'm changing my phase. Make sense? So I'm changing my phase. So I change in the Z2, I'm changing my phase to pi by 9. Pi by 9 is actually 180 by 9, that is 20 degrees. So this angle shown here, this angle will be 20 degrees. So this angle is 20 degrees. Make sense? Again, the next complex number, I'm not changing the magnitude. This is 3. This is not clear here, so let me make this 3. So this is 3. Okay, so the next complex number is e raised I pi by 6. Pi by 6 is nearly 30 degrees. So this is my complex number. This is my third complex number, Z3. See, in all of these cases, the magnitude remains the same, that the distance from here to here is same, the distance from here to here is same, the distance from here to here is same. So what changes is its inclination with the positive real axis. Now, pi by 6 is how much? It is 30 degrees. So, this angle will be 30 degrees. Now again, going ahead, we have our final candidate, Z4. Z4 is 3 e raised I pi by 3. Pi by 3 is 60 degrees. So, again, its magnitude is the same, but its inclination changes. So, this angle will be how much? It will be 60 degree. So, let's say I have a complex number, an arbitrary complex number. Let's call it R. Maybe I should change my color because it will be otherwise difficult for you to read. So, okay, this looks nice. So if I have a complex number e raised to theta, and if my theta is a function of t and it is changing with respect to time, then that means my complex number is rotating in the plane. See, we can think of this is at time t equal to 0, then this is at time t equal to, let's say, after 5 seconds, and let's say this is after 10 seconds, then this, let's say this is after 15 seconds. So my complex number is getting rotated like this. This is the case when theta varies with respect to time. Make sense? So if I have something like this, let's say r e raised I omega t, for the time being, let's say omega is a constant. Let's assume omega is a constant and time is the time which starts from t equal to 0. Then what happens? At each time, my phase changes. That means my theta changes. So both these things are same. Let's say my theta is a function of t. So the function is omega t, which is a linear function. Then that means, so when you see a complex number of this form like this, then it can be thought of as a complex vector rotating with an angular velocity of omega. Make sense? So that's how we physically interpret or geometrically interpret quantities like this as a rotating vector. Okay, we have seen this complex exponential notation throughout this course. So now I want all of you to draw this in an imaginary complex plane. So this is my real axis and this is my imaginary axis. Okay, then it is pretty simple. I have shown it here. So my amplitude or the magnitude is f0 and the phase of my complex vector is omega t. Make sense? And this thing changes every now and then. So physically this is a rotating vector. Now I want you to move further at one step ahead and tell me what will be the real and imaginary components of this thing. So once we take the real component of this, then it will be f0 cos omega t. This will be f0 sin omega t. Make sense? So f0 e raised I omega t is exactly same as f0 cos omega t plus the imaginary part. So before imaginary part I need to put a sin omega t here. Sorry, I missed out an f0, so it's f0 sin omega t. Okay, makes sense? So whenever we have an excitation, because very rarely we come across excitations of this kind, but mostly we will come across with excitation of this kind and this kind, then we can easily take, if it is f0 cos omega t, then we can say that is equal to the real part of my rotating vector. And if it is imaginary, sorry, if it is f0 sin omega t, if the excitation function is f0 sin omega t, then we can easily go ahead and assume that that is equal to the imaginary part of this thing. Make sense? Okay, we talked about excitation. Now again, response against this particular this particular excitation was again a complex number. So now let's represent both these complex numbers in one single plane and see how they are different and how they are aligned to each other. So if you look at closely, this is my excitation. This has a magnitude of f0 as shown here. Then if you want me to, let's say, mark the angles here as well. So I don't want to put so much of detail in the figure, but even then I think it's good to put those details now for a better understanding. This angle will be how much? It will be omega t. So this is the excitation. Now coming to the response, we assume the response to be taking a shape like this, where x of I omega is a complex number that had a definite magnitude and that had a definite phase. So if you see the difference, let's say this is a rotating vector and this is also a rotating vector. So now I'm taking a snapshot, let's say at time t. At any time t, my response complex vector, this is my response complex vector. Let me write it down explicitly. So this is my little x of t. This is not capital X of t. This is my little x of t. This is my f of t. Little x of t is always lagging behind the excitation by an amount phi. We called it phase angle. And the yet another point to note is that the magnitude is different. I have shown it less. Let's say for this example I have shown it less. It may be higher than, it may have this mod of xi omega can assume a value greater than f0. It is pretty much possible, but let's say for the time being it is less compared to your f0. So the magnitude is different and then it is lagging behind an amount phi. Now if I ask you what is the phase of this thing, now you have a phase for this angle will be omega t minus phi. That is the phase. That's why you see an omega t minus phi here and an omega t here. So that makes sense. Now we will move ahead and try to represent whatever quantities we are discussed in the course in this real complex plane. We will try to represent them in this plane. It will be a little bit difficult, but it is worth looking into. Okay, so don't get disturbed by the fact that this looks very difficult to understand. This is a very simple thing, so let me put it down. I am going to represent this particular equation that we have been solving for the last few lectures. I'm trying to geometrically represent the whole equation in a real imaginary complex plane. So this is very simple. We will go one by one. It's not that difficult. We will get to know. It is very simple. So let's say I've shown this vector. This vector represents my kx. Now I hope you remember now x is actually x of I omega e raised I omega t, or the same as mod of x of I omega e raised I omega t minus 5. Okay, so this is a complex number. Since x is a complex number, I multiply it with a constant, which is this, that is the stiffness in the system. Then I will be getting this vector. Okay, this complex vector. Clear? And it will be having a phase of omega t minus 5. That's what we learned just a moment back. Now, one is done. We know kx. Now, what is mx double dot? See, another point to be noted. If I compute x double dot, it will be minus omega square modulus of x of I omega, again e raised I omega t minus 5. See, so now we were computing this particular term mx double dot. We are multiplying this particular complex vector by a scalar. So that direction won't vary. That direction won't change. Then, since there is a minus here, it won't be acting in this direction. This was the positive x direction, so it will be acting opposite to it. That's why I have shown here a small mx double dot here. Clear? So we looked at this quantity, which was this vector. We looked at this quantity, which was this vector. Clear? Now let's go ahead and do this. Look at this. Okay. Now this quantity, to calculate this quantity, there is a constant. It is getting multiplied with x dot, which is yet another complex vector. Now if we go ahead and compute x dot, it will be I omega modulus of x of I omega e raised I omega t minus 5. Now pay attention to this little fellow over here. This is I. So x dot can be also written as, how it can be written? Whenever a complex number is multiplied with I, it is equivalent to rotating it by a 90 degree. So this is, can be, so this particular portion of the vector is oriented in this direction. Now since I am multiplying with e raised I pi by 2, then it will get rotated by 90 degrees. See, now my cx dot gets rotated by 90 degrees to this direction, to the omega t minus 5 direction. Now I have this quantity as well. Now we need to add all these three vectors together. So first take this vector, then since mx double dot was acting in the opposite direction, here we get the resultant one, which is kx minus mx double dot. So it will be of this length. So now we added these two and we got this. Now we want to add this to this. Simple. Parallelogram law. So when I add this portion with this portion, then I will get this. So this is my f0 e raised I omega t. Now I can ask you a simple question. So this particular angle will be my omega t. Make sense? So this is how we appreciate this whole equation of motion in complex plane. This is very helpful at times to have a geometric understanding of how these forces can be represented in the complex plane. See, this particular diagram, this whole diagram is valid only at a single point of time. So what happens, this whole diagram gets rotated at an angular velocity of omega. So this is valid at a time t. After then, my f0 will change, my f0 will rotate like this. Then x has to rotate by this, everything will rotate. So this is just a snapshot at a particular instance. So I hope I was able to drive home this concept. So if you understand it, well and good. If you don't understand it, okay, it's fine, because we may not be requiring it for the further classes. So it's a good concept to understand. Even you don't get a feel for this, it's okay. It will take time.